All right. Hello, my name is Austin Burba, and my article for midterm one was about algae-based fillers for polymer 3D printing. You can see one of these over to the left. This is a PETG mixture with 10% algae. The title for my article was Technological Evaluation of Algae-Based Fillers for Polymer 3D Printing. The authors were Fiedler, Schmeg, Fisher, and Droder. This was in the Sustainability Journal, volume 15-5, year 2023, page 4039. Next, I'm going to go over the specific scope of the study. The scope of the study was to test properties of algae-based filaments and determine which algae type is the best. This was done through different thermal tests, mechanical properties tests, actual measurements. And the key question that was addressed was how much algae can be used before specific properties are lost and which algae should be used. Next, I'm going to go over the methodology. The first thing being the models used. This is actually what was 3D printed to test with. The first one was a 57 by 10 by 2.5 millimeter, just regular rectangular specimen. This is a specimen that was used in the dynamic mechanical thermal analysis, as well as the 3-point bending. The next model used was a standard type 1A tensile test piece. This is what's pictured over to the right. It's just the pieces that you'd use for a regular tensile test. The dimensions on this was 170 by 20 by 4 millimeters. Some of the tests that were done was, like I said earlier, the dynamic mechanical thermal analysis. This tells us how much weight we would lose as we get closer and closer to the working temperature of our filament. The tensile test, the 3-point bending test, and microscopic images to see what our surfacing looks like. And the materials that we used / surveyed is the spirulina and chlorella algae. These are the two different algae that were looked into to determine which one responds better in the filament. And the thermoplastic PETG, this is the baseline filament. This is what the algae was put into or mixed into to create the filament. The next thing I'm going to go over is the key result from study one. This is the first result we had is based on the question, should spirulina or chlorella be used as the algae filler? This was determined by heating up the filament and seeing when weight loss and gases were put off by the different types of algae. As you can see, pictured on the left is a spirulina. As you get closer to that 230 degrees Celsius, this is the PETG working temperature. You see that there's very little weight loss in this area. Now, on the other hand, whenever you look over at the chlorella, there is a decent bit of weight loss in this area. Judging based off these graphs, the authors of the article decided that the spirulina was the algae to go with when looking in the filaments. Like I said, spirulina algae emits very few gases of weight in the PETG working temperature range. This means it's the algae for the job. The next thing I'm going to cover is another key result from the study. This result answers the question, what % of algae weight can reliably be used in the filament? There was three different types of algae filaments used in there, a 10% algae weight, 20% algae weight, and 30% algae weight. As you can see in the graph to the left, a neat PETG, meaning no algae used, has a regular ductile response with necking, as one would expect. The 10% algae weight test specimen has this same ductile kind of response. So this is good when looking for a bio-based filler. Now, on the other hand, the 20% and 30% weight does not have this response, but it has more of a brittle response. So we decided that, or the authors decided that the filament with 10% algae weight loses very little mechanical properties and print quality, so it should be the one to roll with. Just to summarize things up, algae is a competitive bio-based filler candidate. As you can see, it keeps those ductile properties that are so sought after as engineers. 10% is definitely the algae weight that should be that should go with because it keeps those ductile properties. There's various environmental advantages to these algae use. One being that it cancels out the CO2 that's used whenever it's thermally recycled, because as it grows, it takes in CO2. The next thing is the material properties do not change with lower amounts of algae. And the only critique I have for this article was that the authors did not do a proper cost and sustainability analysis. I think they had the information to do this, but they did not conduct one, but rather push it on to the reader. That's all I have. Thank you.